In this video, we're going to take a look at the disjunction rules in Fitch-style system. Let's take a look at them. Alright, let's start thinking about these disjunction rules first in terms of when a disjunction is true. A disjunction is true just in case at least one of its disjuncts is true. So what that means then is if we're given a proposition, that is, we get to accept a certain proposition that's to be true in our proof, maybe the grass is green for instance, then it'll turn out that we can introduce any disjunction in which our given proposition is one of the disjuncts. And that's because the truth of that proposition will ensure that one of the disjuncts of the disjunction is true. So since we get to accept the grass is green to be true, then if I create a disjunction, say the grass is green or the snow is white, then since this is at least one of the disjuncts of the disjunction, the entire disjunction is going to have to be true as well. And it doesn't matter which disjunct, in this case the grass is green, is. It just matters that it's in that disjunction and it will force that disjunction to be true. Alright, so let's take a look at how this second rule ends up falling out of when a disjunction is true, the meaning of a disjunction. So a disjunction, we said, is true just in case at least one of its disjuncts is true. So this time, let's say we start off knowing or getting to accept some disjunction is true. Maybe it's that the water is warm, or the sand is warm, or the people are tan. We know that this is, so the idea here is we get to accept this disjunction as being true, and based off of this, that means we know that at least one of its disjuncts is true. So at least this is true, or this is true, or this is true, or maybe two of them are true, or maybe all of them are true. But all we can tell right now is that one of them, at least one of them, is true. That's all we know at the moment. But let's say that we isolated each of these, and then we had a series of valid inferences that go to the proposition that it's sunny outside. Well, notice then that it doesn't matter which one of these is true, which one of our propositions is true, or whether all of them are true, or whether just two of them are true, because a valid inference goes from all of them to the proposition that it's sunny outside. It's got to be the case that it's sunny outside, because one of them being true, there is a series of truth-preserving inferences that gets us to the claim that it's sunny outside. So that leads us to this idea that if a proposition can be proved from each of the disjuncts of a disjunction, then it can be inferred from that disjunction. That is, we'll get to know that it's true. Alright, let's take a look at the formal counterparts of these in the Fitch-style system. Alright, so the first formal rule that we're going to take a look at with respect to disjunction is disjunction introduction. And it tells us that you can go from any proposition, whatever that proposition is, to any disjunction that has that proposition among its disjuncts. And that's exactly what this diagram here tells us. So up here, this is representing to us that we get to accept the proposition P sub I as being true. this is telling us that then we can make the inference some disjunction that has pi in it by the rule disjunction introduction. And then we just have to cite where the step that proposition p sub I, whatever it is, came from. Now many students don't like this inference because it seems like we're going from something that we know is true to then a proposition that in some sense contains less information, because this just says that at least one of those propositions is true. But we already know that that one is true, right? But you need to don't concern yourself with that so much. The reason why this is a good inference is because it's truth preserving. This being true guarantees that at least one of the disjuncts in this disjunction is true, namely this one, right? So since a disjunction is true, just in case at least one of its disjuncts is true, the fact that we know that that disjunct is true means that we know that the disjunction itself is true. So that's why it's a good inference. All right, let's take a look at this example of this rule being applied here. Our premise is that A is a cube, and since that's our premise, we get to accept that as being true. Well, since we know that A is a cube is true, we know that this disjunct is true. And since we know that disjunct is true, we know that the entire disjunction itself is true. So we've made that inference from 1 to 2, and I have to cite it as disjunction intro, and then I have to cite the step of the disjunct that I'm relying on that guarantees that the disjunction that I've inferred is true. All right, let's turn to the next disjunction rule in Fitch-style system, disjunction elimination. All right, so disjunction elimination tells us that if we're given a disjunction, that is, we get to accept a certain disjunction to be true, and if we demonstrate that some sentence follows from each of the disjuncts, that is, there is a set of valid inferences that moves from each of the disjuncts to S, then we can infer S. All right, so how do we represent that in Fitch-style system? Well, here we get to accept some disjunction to be true. So the only two disjuncts that we are seeing here is P sub 1 and P sub n. This is just representing that it could be however many disjuncts. What we'll then have to do is insert our own assumption. So the way that we do that, and I'll show you how to do that in Fitch, is we make this subproof. And we say, basically what we're representing here, what we're saying to ourselves is, let's see what happens if we assume P sub 1 to be true, which happens to be one of our disjuncts. And now we see that we can get to sentence S. All right, so let's say we keep doing that for all of these in-between disjuncts, however many of them there are. But not all, but also we make an assumption for P sub n, our last disjunct here, and we're able to show that we can validly infer S from it. then because we're able to do that for each of our disjuncts, we can infer S. And notice that S is back outside of these subproofs here where we had the assumptions. So it goes back out to the regular proof. And what that represents is that we really get to accept it to be true now. We've gotten it in a legitimate way. All right, so the way we cite this then, we have to say, hey, we're using disjunction elimination. We have to point out the disjunction from which we get all the other disjuncts. And then we also have to say, hey, one of our assumptions led to S. Another one of our assumptions led to S. In fact, we have to show that all of our assumptions led S that correspond to the disjunction or disjunction. And if we do that, we get to have S. And again, the reason why that's the case is because in saying that the disjunction is true, we know that at least one of the disjuncts is true. So if I can show for each of them, for each of the disjuncts, that there's a set of truth-preserving inferences that lead to a proposition S, then I will have made sure to cover all my bases. I will have been sure to include the at least one disjunct that is true in demonstrating that S follows from it. So that's why it's a good inference. All right, let's turn to take a look at an example of disjunction elimination being used. All right, so in this example, we start off with the premise that either both A is a cube and B is large, or B is large. So what we have here is a disjunction in which one disjunct is an atomic statement, and where our other disjunct is a complex proposition, complex statement. So we know either this is true or this is true, or they're both true. But we don't know which one of those options. We only know one of those cases, that at least one of those is true, I mean. So what we are doing in step 2, we have introduced the assumption using this subproof here. We have introduced the assumption that both A is a cube and B is large. So notice that's corresponding to the first disjunct that we have here. And the next thing that we do is we show that by conjunction elimination, that it's got to be the case that B is large. Right? If it's the case that both A is a cube and B is large, then under our assumption that we've introduced, B is going to have to be large as well. Okay, so then we have this gap here between these two subproofs, and that shows that we are introducing another assumption that's not any longer assuming that A is a cube and B is large. That's why they're separated. And notice that B is large just is the very same sentence here under our assumption. So under both of our disjuncts, it turns out that B is large. So just by knowing that either both A is a cube and B is large, or B is large, we can infer that B must be large. So we then cite the rule conditional elimination. We cite the fact that the disjunction and where we are getting the disjuncts from, and then we we say to somebody who's reading the proof, 2 to 3 is a valid inference, where 3 is the proposition that ultimately we want to infer. 4 through 4, if you will, it just is the same proposition that we want to infer. Therefore, this is, in step 5, a legitimate inference. Alright, so what I want to do now is walk you through some examples of disjunction introduction and disjunction elimination in the Fitch computer program. So let's turn to doing that. Alright, we're going to take a quick look about how disjunction introduction works in Fitch here. We have two premises starting off. So we get to accept G as being true, and we get to accept that it's true that both A and not the case B is true. Alright, so let's start with G. Since G is true, as long as I put G somewhere in a disjunction, because I know I get to accept G up here to be true, then I'm guaranteed that this disjunction that I created that has G in it is also true, because a disjunction is true when at least one of its disjuncts is true. Alright, so I can't just hit the check without applying any sort of rule. I find disjunction introduction. I can't even just put that. I also have to cite what it is that's making this whole disjunction true, namely the fact that G up here is true, letting us know that this G is also true. Okay, it doesn't matter where G is in the disjunction, whether it comes first or whether it comes second, or it's in the middle somewhere, so on and so forth. It just has to be there, just has to be in the disjunction somewhere to guarantee that the disjunction is true. Alright, we can also move from an atomic sentence such as G to a disjunction that includes compound propositions as well. So that'll still be a good inference, because even though this is a compound, this disjunct is a compound proposition, namely one that's a conjunction, this G, being that we get to accept it in true by number 1, is still going to make the whole disjunction true. And that goes on and on for whatever compound sentences that we make, as long as it serves as a disjunct in the disjunction that G is also disjunct in. Alright, so I also want you to be aware that the same sort of things that we've just looked at apply to compound propositions as well. So by putting parentheses around both A and not the case B, since we get to accept that very same proposition to be true in step 2, premise 2, then we can make any disjunct that we want out of it as well, or disjunction rather, out of it. And so so on and so forth for all the same sort of things that we were looking at with G. That's going to apply to a compound sentence such as A and not the case B. We can make all those same sort of moves. So very quickly, for instance, it doesn't have to be the first disjunct. All right, let's take a look at some examples of disjunction elimination in Fitch. All right, so let's suppose that we came across an exercise problem that wanted us to prove that A is small follows from the proposition that either both A is small and A is a dodecahedron, or it's not the case that A is large and it's not the case that A is medium. All right, so one thing to note, or one of the first things to note, is that the proposition that we have here is a disjunction where a conjunction is its first conjunct and a conjunction is its last conjunct. Well, because this is a disjunction and is a premise, we know that at least one of those disjuncts is true. So we can ask ourselves, well, what would happen if we assumed individually that both of those were true? So I hit Control P to make this assumption, and it's an assumption that we are introducing. So we don't just get to have it, but we're asking ourselves the question, well, what if this was to be the case? You can also introduce subproofs by selecting this option here. All right, hit Control A to get another step and Control E to get out of that subproof, as this says here in subproof. And I'm going to hit Control P to give me another assumption where when I'm assuming this, the second step, it's no longer being assumed when I get to the third step, and when I'm at the third step and anything that's underneath it, it won't be assumed or won't hold for step 2 as well. They're independent of one another. So what I like to do is go ahead and put assumptions for all of the disjuncts in question. Here we only have 2 disjuncts, so I've only made 2 assumption steps, 2 subproofs. Alright, so that's one of our disjuncts, and this is our other one. And based on what we've said, we know that either this sentence is true or this sentence is true. So either the sentence in step 2 is true, or the sentence in step 3 is true, or maybe even both of them are true. We also, if you recall, we're trying to prove that A is small. Well, at step 2, I can see very easily it's A being small is going to follow because the assumption that we made is A is small and A is a dodecahedron. Well, in order to show that A is small follows from that, we use conjunction elimination. And we can double check our work as we're going through, and indeed that's a good inference. Alright, I can already see just by this conjunction that if A is not large and A is not medium, it's going to have to follow by the meaning of large and medium in Tarski's world that A is going to have to be small. But normally we can only use anicon on literals, not on atomic sentences, or I'm sorry, not on compound sentences. So let's go ahead by, again, conjunction elimination, break up these sentences, pull both of these conjuncts out. And now that I have both of those conjuncts out, I can use anacon on them to show that A must be small under that assumption. Great, so if this is true, then at least one of these is true, either 2 or 4. And if 2 is the one that's true, then it's got to be the case that A is small, as is shown in 3. But maybe this one's false. Well, that doesn't matter, because if this one is true, then again I can show through a series of valid inferences that A is small. So it follows then from 1 that A really does have to be small. And now we use disjunction elimination to show that. I need to cite the disjunction that we were relying on, and we need to cite the fact that from the assumption of all of our disjuncts, in this case just 2 disjuncts, that we can get to the same sentence. In this case, A is small, as in 3 and in 7. And we check the proof, and then we can see that A small does in fact follow from our first premise. Alright, that wraps up this video on the formal rules of disjunction in the Fitch-style system. I hope it proves useful.